let's start with our warm-up problem. So Willy Wonka is introducing a new candy called the black hole. Now this is a dark chocolate confection which is the shape of a sphere. And it has a diameter of 2 centimeters. Okay, so what do we have? We have our 2 centimeters. All right, so here it is. It's 2 centimeters is the diameter. So that's all the way across. It's 2 centimeters. And the center is hollow. So what does that mean? Well, it's not solid chocolate. So there's like a smaller sphere in the center that's been punched out. So it's like you take a big sphere and you pick out a smaller sphere from the inside. So that's our shape. Now, in keeping with this over-the-top tradition, Wonka has perfected a method to get the density of a chocolate to be 1 over rho grams per cubic centimeter, where rho is the distance to the center. And yes, that does mean we achieve infinite density at the center, which makes this a true black hole. Now, Wonka has decided that the black hole should have a weight of 4 grams. So, all right. Now, of course, the physicists will say, grams aren't weights, but that's all right. We're mathematicians. We'll say grams are weight. Find the thickness of the shell of the black hole that Wonka will need in order to achieve this goal. In other words, what's the difference between the radii? All right. So, there's one thing I didn't write down, which I should. We know our density at any given point is 1 over rho, where rho is the distance to the center. And we want our mass, which is our stand-in for our weight, to be 4 grams. Now, looking at this problem, it says, all right, what are we trying to find? Well, we're trying to figure out how do we make this candy to weigh exactly 4 grams. So we're after to sort of set the parameters of the shape. So this is a problem where we're giving the mass, and what we have to do is we have to figure out what's the shape that it corresponds to. Where it's not just sort of any arbitrary shape, it's the shape which is between 2 spheres. Now, looking at this problem, we're going to do integration, but how should we go about doing integration in this? Is there some particular idea we need? We need spherical coordinates. Now, what's the clue that we should have spherical coordinates? Yeah, the fact that we have a sphere. That's a big clue. The other big clue is our density, because our density is phrased as 1 over rho. Now, that's a type of phrasing where it's saying our density is given to us in terms of spherical coordinates. So we should use our spherical coordinates. All right. So we have that our mass, that's equal to the integral over our region. I'll call it S for our solid shape, of our density, dV. So, integral, density, 1 over rho. What's dV for spherical coordinates? Rho, sine of phi, d rho, d phi, d theta. Yeah, okay, good. We still remember it. All right, good. Sticks in the head after you do it for a while. Now let's talk about our parameters. So let's talk about theta. Where will theta go between? 0 and 2 pi. Now the theta, if we were to think about throwing in some axes here, the fact that it goes 0 to 2 pi just says we have this full revolution around the z-axis. So when you see the same shape all the way around when you talk with respect to the z-axis, that means your integral goes from 0 to 2 pi. How about phi? Where will phi go from? 0 to pi. Because remember, phi talks about how you're coming off of the positive z-axis. So phi equals 0 is straight up. And then you're going to go down to phi equals pi, which is straight down. And so we're doing the whole shape. So we go from 0 to pi. Now, what about rho? Well, what we know is that the diameter is 2 centimeters. So how far is it to the outer shell? It's 1 centimeter. How far is it to the inner shell? Well, the answer is we don't know. That's what we're trying to find out. See, we're trying to find the thickness of the shell. So that we don't know what the distance is. So we need to give it a name, a variable name for right now. What should we call it? Let's not call it x, because x is oftentimes with coordinates. A, okay. All right, we'll chant our inner key. What's the thickness? A. All right. There you go. Now, this is not so bad. Now, even though we're thinking of A as something that is to be set to the right parameter, it really will be a constant, which means that as we look at these three integrals, it's the nice kind of integrals, where it's numbers to numbers, which means we have the ability to really pull this apart. So, separating this into three pieces, we get 0 to 2 pi, that's the d theta, 0 to pi, that's sine phi. Now, and then the last one, d phi, and then the last one, a to 1, that'll be the rho. You have 1 over rho and rho squared, which becomes rho, and that will be d rho. What's the first integral going to give us? 2 pi. The second one, well, what's the integral of sine? Negative cosine, evaluated from 0 to pi, and if you plug in pi, you'll get negative 1. Subtract, if you plug in 0, you'll get 1, but there's a negative. Okay, so it ends up being 2. The last one, well, integral of rho, d rho, 1/2 rho squared. And then we're evaluating from a to 1. So this becomes 1/2 times 1 minus a squared. All right, so if you multiply the 2 pi times the 2 times the 1/2 times 1 minus a squared, well, the 2 and the half cancel. So this becomes 2 pi times 1 minus a squared. Now, that's our mass. What do we know about our mass? It's got to equal 4. So that equals 4. So this is great. 1 minus a squared is 4 divided by 2 pi. That's 2 over pi. And then we move stuff around. We get that 1 minus 2 over pi equals a squared. So a is equal to the square root of 1 minus 2 over pi. We don't need the negative because a is measuring the distance out. Now, is that our answer? No, because you always are suspicious when I ask that question. Because, it's like, no, that's not our answer. But it kind of feels like our answer. What were we looking for? Let's be careful here. The thickness. So that A is how far out from the center, but that's not the thickness. To find the thickness, we need to find the difference. So the A is measuring the length here. The thickness is the part from the outer shell. So to get our final answer, what do we do? Yeah, 1 minus that. So our thickness is 1 minus the square root of 1 minus 2 over pi. And that's the answer. All right. Good times. Now you know, yes, math does have applications. Designing chocolate. Important stuff. So we've been talking about a couple of different ideas that we've been playing with, where we've talked about different coordinate systems. We've talked about polar coordinates. Last time we did cylindrical and spherical coordinates. And we saw that when we changed coordinate systems, that we had these sort of extra pieces showing up. So, for example, in polar, we had this r term. When we went to cylindrical, the r was still there. When we went to spherical, we introduced this rho squared sine of phi. So we have these pieces showing up. And I should say these are not the only time that we've seen this. If we go back all the way to when we were young and innocent, we did Calc 1. And we learned about this idea of substitution. And so if I had this integral a to b of f of x dx, it would be the same as the integral of f of g of u times g prime of u du, and the bounds would need to be updated appropriately. So that there was this extra term g prime of u. And this g prime of u actually serves the same role as what these terms are serving here. So there's this question, where are these coming from? How do we figure them out? What do they do? So when we do our change of variables, we always have to sort of account for a couple of things. And some of them are easier, some of them are harder. Some of the things which are probably hardest for us is figuring out how do we describe our shape. So what are the inequalities that come into play? The function is usually not so bad, but the piece at the end, what is that telling us? Well, we have to figure out what that means. So here's sort of a motivation. So suppose we are going between two different coordinate systems. So here's our picture. Originally, we had our picture, say, in the xy plane, and it was some sort of weird, slightly warped shape. And now what we're going to do is, by being very, very smart and creative, we're going to come up with a new kind of coordinate system. We'll call it u and v. And what happens is every single point in this region corresponds with a point in that region. So there's a map between these two. So in other words, I can go back and forth between these two. As an example, if I take this point in the corner here, that is a point x comma y, well, I can figure out I have some function u, which depends on x and y, and some function v, which depends on x, y, and that tells me that maps to that corner point there. So what I want to do is I want to say, okay, how do I translate back and forth? Now, you'll see what I've done is in both coordinate systems, I've put in a grid. And what the grid does is it actually does map back and forth. And I've highlighted this one little piece. Now, what we want to do here is we want to understand what's happening to the size of that piece. In other words, as we change coordinate systems, we've got to account for the size of our small parts. Because things might dilate, get larger, or contract and get smaller. And so we need to appropriately scale the contribution from that piece. So what we're trying to figure out is, okay, remember that integration says let's break things into small parts. How do we appropriately weigh each part? Because when we change our coordinate systems, some parts might get smaller, some parts might get larger. So what we've done here is we said, okay, let's suppose we take a really small piece. So there's that little small piece there. It's really easy to understand. It's a rectangle. That corresponds to something over here. It's a little bit warped shape, but if you look at this shape and say, okay, when I look at a small piece, it's not quite so curved. In fact, it looks awfully like a parallelogram. So that a parallelogram is a reasonable approximation to the piece. And now we're like, aha, parallelograms, we know how to work with those. Because we did something with parallelograms very recently where we talked about surface area. So you're going to see it's a similar idea coming into play here. So what we want to do is we want to figure out, okay, what does this parallelogram look like? So one way you can figure it out is you can say, all right, I just need to figure out what's the vectors that are involved on these two sides. So I have here, this is in the UV plane, and I'm going to map over here into the XY plane. And so I say, okay, well, if I want to figure out what's happening here, well, this side is going to tell me about my change in U. So the vector here comes from saying, what's happening to my change in U? So there's a change. How does X change with U? How does Y change with U? That determines that vector. In a similar idea, this side over here, well, that's going to map over to that side. I need to know, what does the change in V translate into? So the answer is the following. The sides of the parallelogram, and I'll just move this up for a second here. So this side of the parallelogram right here, which came from understanding what's happening to this change in U, it's approximately, the parallelogram, it's partial x, partial u, delta u, partial y, partial u, delta u. So I'm changing u. I want to say, how does the x and y change as I change u? And that's the answer. This other side, that comes from the change in v. So partial x, partial v, delta v, partial y, partial v, delta v. That's the parallelogram, which is a good approximation for that piece right there. So now, if I know how to find this area, that's delta u, delta v, how do I find this area? What do we do to find the area of a parallelogram? Cross product. However, can we take the cross product of these two vectors? And why not? It's two-dimensional, right? Cross product, we need what? A three-dimensional vector. We've got ways to solve that. So how do you solve that? Well, toss on a 0. So we toss the 0 onto the end. Now we're going to take the cross product of these two vectors, take the magnitude of that cross product. That's going to find us the area. So that area, that's telling us how much we're locally expanding or contracting. Now if you do this, there's a couple of things you can do that are pretty easy. First thing is, from the first vector, pull out this delta u. From the second vector, pull out the delta v. And if you do all that, what you end up with is the delta u, delta v comes out towards the end, and the rest of it becomes a 2 by 2 determinant. Now originally it's a 3 by 3 determinant, but you can do what's called cofactor expansion, and you end up with a 2 by 2. All right. Now you'll notice I have this little thing underneath it. This has a name. So we call this the Jacobian. This is named after a mathematician named Jacobi. So it's Jacobian. So the Jacobian, that's measuring how much we're expanding or contracting. Now here's the nice thing about the Jacobian. It's sort of the nicest, most forgiving thing you're going to see in Calc 3. By which you might say, how do I remember which partial derivatives go where? And the answer is, almost anything you write down will work. So if you look at what's happening here, you'll see that the x and the y, the x's are in one column and the y's are another column. So it's like go x and y. But then, if you say where does u and v shows up, they go in the rows. So u and v. So all you need to remember is that one set of coordinates go in the columns. So partial x, partial y. But you could have done partial y in this column and partial x in that column. And then your other set of variables fill up the rows. And as long as you do that in any order, it won't change the output. Because the absolute value on the outside takes care of any sign thing that you might introduce. So that's the big idea. And I will point out that there's this sort of nice idea that saves us a little bit of work. And the nice idea says, hey, we're looking at how much we're expanding and contracting. What happens if I do the following? If I go from here to there and back again, what's my net effect? Well, my net effect is I haven't changed. So you can think of it as there's been zero change, which means the amount of expansion and contraction, well, if you think of it as a multiplicative factor, we would scale by 1. Well, what that translates into is it says, if I'm looking at the two Jacobians, which measure my expansion and contraction in the different directions, when I multiply them together, I get 1 out. So it's sometimes a faster way to compute things. And that can save a little bit of work. So let's do an example. Let's do a change of coordinates. So suppose we do the following. Let's let x equal r cosine theta, and let's let y equal r sine theta. And I want to find the Jacobian of r and theta. So, according to this, what do? Well, we're going to take the determinant. This is what this means, the determinant. And really, it's the absolute value of the determinant. So we're going to take partial x, partial r, and then we're going to do partial x, partial theta, partial y, partial r, partial y, partial theta. All right, let's fill this up. What's the derivative of x with respect to r? It'll be cosine theta. What's the derivative of y with respect to r? Sine theta. What's the derivative of x with respect to theta? Negative r sine theta. What's the derivative of y with respect to theta? R cosine theta. So now I want to take this 2 by 2 determinant. So cosine theta times r cosine theta is r cosine squared theta. So you multiply these together. Subtract r sine theta, negative r sine theta times sine theta is negative r sine squared theta. Well, minus minus makes this plus. What else can we do? Pull out an r. Cosine squared plus sine squared. Does that simplify any further? Yeah, this becomes 1. Which means we end up with an r. Now, that might be like, ooh, this sounds a little bit familiar. Why does it sound familiar? Well, what have we done? Well, what are we doing here? Changing into polar. And so what the Jacobian is telling us is what's going on here is what we really should say is that delta x, delta y is really approximately this. Or when we translate in the limit, dx dy would be equal to the Jacobian, which is r, times our dr d theta. And therefore, now we're like, aha! So there's where the r comes from. It's the measurement of how much you're expanding and contracting locally. Okay, so now we're going to put this all together. All right, so this is going to take us a minute here to understand, but then we'll spend a little bit more time practicing. So I have my 2 regions, and what do I want to do? Well, I now know that on the left-hand side, that a piece of my area looks like delta u, delta v. On the right-hand side, well, I look like a delta y, delta x. But what I know, because of the Jacobian, is that delta y, delta x is approximately that Jacobian times delta u, delta v. So here's our basic idea. Suppose I want to find the integral over this region R. So I'm after the integral over my region R. Now that's not so bad. We know how to do that. So if I want to find the integral over a region, I break it up into little tiny pieces. I add up what's the contribution for each piece. Now what we say is, all right, let's rewrite this sum. And the way we're going to rewrite the sum is we're going to say, okay, so instead of breaking things up over here, I really want to understand what it looks like over here. So I'm going to use my S as a guide to understand R. So I know, for example, delta y, delta x, I can replace that by the Jacobian delta u, delta v. And my function, x, y, well, I can really say I can use these points here in the grid to help understand points over there, which becomes the function of x of uv, comma y of uv, times the Jacobian of uv du dv, where what we're doing is we're using our grid over here to break things up. So that says we're integrating over this region S. And that's our change of variables formula. So in general now we can switch our coordinate systems. All right, so that's the idea. So this Jacobian of uv acts the same way as when we took just substitution in single variable calculus. We had that sort of the derivative term showing up. That's what the Jacobian is doing. Now, what's the process? Well, it's sort of several steps. The first step, if we're going to do a change of variable, is you identify the substitution to make. So in other words, I've got to come up with a new set of coordinate systems. So how do you do that? Well, one of the ways you would do it is, suppose you just saw a problem in the wild. You'll look for some function that's on the inside. And you might say, oh, there's this complicated expression on the inside of a function. That might be a good candidate for a new variable. So that would be a changing of the way I describe coordinates. Or you might see some really exotic boundary curves. Okay, let's make that kind of boundary curve. That might help me make a new coordinate system. But I'll tell you the most common way that you'll identify the substitution to make is the following. And it works pretty much almost all the time in the problems you're going to see. You're going to look for the following phrase. Given u equals ... and v equals ... So the good news is that step one, we're just going to give it to you. Because I will tell you that coming up with the right substitutions is very, very tough. And if you gave one to an instructor without telling them substitutions to make, 50-50 they won't be able to figure it out. But that's okay. You can learn this. It takes practice, but we don't want you to be stressing about this part. So when you're trying to figure out what's the right substitution to make, just read the problem, and it'll say, by making the substitution, u equals this, and v equals that. Now we say, okay, we've identified our substitution, and we remember that every integral has three parts. So the second step, you'll see there's a 2a, a 2b, and a 2c. And really, it's just saying that we're going to break all our integrals up and do the three parts individually. More or less, you really don't have to go in this order. You can go in any order you want. That being said, I do think it's very useful to find the Jacobian first, because it can have an impact on how you write the function. And we'll do some examples. So what are the three pieces of the integral? Well, there's the how do you expand. So that's why you need the Jacobian. That tells you how you're expanding or contracting. There's the how do you rewrite the function. And then there's the how do you change your bounds. And those are the three parts. So that's why there's 2a, 2b, 2c. Then the third step is you put everything together. So it's actually not so bad once you understand the process. Okay, you've identified the substitution. You carry out what's the Jacobian. You rewrite things. And life is good. Any questions before we go into examples? All right. Well, I hope that the examples will help make things clear. So let's try some examples. So let's find the following. The integral from 0 to 1, the integral from x squared plus x to x squared plus 1 of 6x divided by 1 plus y minus x squared cubed dy dx by doing a change of variables with u equals y minus x squared and v equals x. Now, this is a problem where a change of variables is pretty much required to make any progress. Because if you were to try to integrate this with respect to y, you'd have a tough time. Because what would happen? Well, you have a y cubed downstairs. And that's the only place where y shows up. So that would be tough. What if you integrate with respect to x? Well, you could try making a substitution, but you still end up with a u cubed downstairs, which is not going to be pleasant. It's still tough. I mean, there's no clear way to start this integral as it's given. And that's why we do this substitution. We don't do it just to like torment students with like, well, ha, here's a way we can get a lower average. No, we want to do this because it helps us solve problems. That's our goal, is let's try to make problems that we can't solve into problems that we can solve. All right, so our step one is identifying our substitution. That's pretty straightforward. There it is. There's our substitution to make. All right. So now we go and we have our choices. Do you want to do the Jacobian, rewrite the function, or determine the new bounds? Which one do you want to do first? Jacobian? All right. Let's do our Jacobian. So, how do we find our Jacobian? Well, Here's how I like to do it. And so this is a slightly different way, but that's all right. I'm going to take this set of partial derivatives. So I'm going to look at partial u, partial x, partial u, partial y, partial v, partial x, and partial v, partial y. All right, let's find these partial derivatives. What's the derivative of u with respect to x? Negative 2x. What's the derivative of v with respect to x? 1. What's the derivative of u with respect to y? 1. What's the derivative of v with respect to y? 0. So what's our Jacobian become? Well, if you take this determinant, what do you end up with? You'll end up with negative 1. But remember that Jacobian, really, you always take the absolute value because it's always about size. So our Jacobian is 1. Actually, this is our Jacobian of xy. But the nice thing is, if you know the Jacobian of xy, you get the Jacobian uv as a freebie. Now that's great. The fact that we have 1 says, ha ha ha, that part's not going to come into our equation. So that's good. All right, so our Jacobian is 1. Life is good. They won't always be 1. Don't worry. We'll do some other ones. Now, how about the function? Okay, so here's our function. What we want to do is we want to rewrite it in terms of u and v. So the way I like to do it is I say, let me try to figure out the pieces, if I can figure out ways to write the various pieces in terms of u and v. So notice, for example, you have this y minus x squared here. What do you know about y minus x squared? It's u. So that says that the denominator I can replace by 1 plus u cubed. Now, 6x. Well, what can we do with 6x? Well, yeah, because x equals v, so that can become 6v. And now, that becomes our function. I should have put a little side note here because of our Jacobian. I'll do it right now. What this tells us, our conclusion about our Jacobian is dx dy is the same as du dv. That's what the Jacobian being 1 tells us. Now the last part is we've got to figure out the bounds. So that means we've got to draw the current bounds. So let's sketch the current bounds. What do we know about our current bounds? Well, what's true about x? Yeah, we go from 0 up to 1. How about for y? What does that do? Well, we start at x squared plus x, and we go up to x squared plus 1. That's what our current bounds give to us. So we need to sketch this region. Well, x squared plus 1 is probably easier to sketch. X squared plus 1 is our parabola, but we shift it up by 1. So it will look like that. And I'm only going from 0 up to 1. How about x squared plus x? What does that look like? It's also a parabola. Now, it might help to identify what happens at 0 and 1. Where are we at x equals 0? We're at 0. Where are we at x equals 1? We're at 2. Now notice, where is x squared plus 1 at x equals 1? 2. So they both intersect. Apparently my scale is not quite right. But pretend that these were equal in size. They both intersect at the same point. So it's a parabola that does something like that. If you were to look at the other intersection for x squared plus x, where does it hit the x-axis? It's at negative 1. So it's a parabola that's been shifted down and over. All right. So our region is this sort of, let's say, somewhat skewed triangle. And the reason I say it's a triangle is because there's 3 sides. Now, to figure out what happens to our region, I want to identify all the curves that are bounding the triangle. So let's list them. How about this left-hand side? What's that curve? X equals 0. How about the top one? What's that curve? Y equals x squared plus 1. How about this bottom curve? What's that? Y equals x squared plus x. So what happens is these are my boundary curves written in terms of x and y. What I'm going to do now is I'm going to take these boundary curves and I'm going to say, let me try to rewrite these in terms of u and v. So let's start with a simple one. X equals 0. How can I rewrite that in terms of u and v? I can write it as v equals 0, because v equals x. Okay, now this one might take a little bit more. Y equals x squared plus 1. When we look at u and v, we say, okay, I want to get something that looks like a u or v involved. So what can we do? If you subtract the x squared over, you get y minus x squared equals 1, which becomes u equals 1. Now how about y equals x squared plus x? Well, let's subtract the x squared again, because we like y minus x squared. So you get y minus x squared equals x. What does that become? U equals v. So that says that my boundary curves in my uv plane, so this is my xy plane, so when I go over to my uv plane, which I'll mark now, I have the three curves. I have v equals 0. Well, that's the axis here. This is v equals 0. I have u equals 1. And then I have u equals v. So my region will be the one that's contained by those three curves, which says that our new region is going to be this triangle. So that's our new shape. So we're now ready to update our integral. So it's going to be an integral, our new function, 6v over 1 plus u cubed, dy dx is going to become du dv, or it could be dv du. Let's look at our region. What should we integrate? What's probably the better order to integrate? Or let's even just look at this function. Do you want to integrate first with respect to v or first with respect to u? You probably want to first integrate with respect to v, because integrating first with respect to u, it's possible, but it'll take us this class and the next class. We don't want to do that. We want to do something that's simpler. So this is certainly an easy integral with respect to v first. So we're going to do dv du. So where does u go from? 0 to 1. Now, if I pick a u, where does v go from? 0 to u. Because these are v bound, so I need v equals something. V equals 0 and v equals u. So it actually says to find, so we have to keep going. When we integrate the inside with respect to v, what do we get? 3v squared over 1 plus u cubed. Evaluate that from v equals 0 to v equals u du. Well, if you plug in 0, you get 0. And if you plug in u, you'll get 3u squared over 1 plus u cubed. And that one's not so bad. What does that become? Natural log of 1 plus u cubed from 0 to 1. When we plug in 0, we'll get log of 1, which is 0. And when we plug in 1, we get log of 2. And there's our answer. So by changing our bounds, we changed from a problem that was very intimidating to one which was not so bad. And that's what we want to do. We want to change the things which are not so bad. We prefer things that are not bad. It's our natural state. Okay. So, by substituting u equals x squared plus y and v equals x squared minus y, find the following. All right. Well, this is going to be great. Okay. Well, the first step, figure out our substitution. That was good. I like that step. So we know what our substitution is. Now, we got to find the following. Well, let's start. The nice thing is these are both the same function. It's just that we have two different regions. I'm not sure why. Well, we'll find out. We'll get there. We'll figure it out. So let's start with our Jacobian. So I'm going to compute our Jacobian here. So I'm going to look at u sub x, u sub y, v sub x, v sub y. So this means take the derivative of u with respect to x. I can use different notation. And like I said, Jacobian is very forgiving. If you might say, but wait a second, in the previous slide you did such and such. All right, no. It's very forgiving, very forgiving. Okay, what is u sub x? 2x. What is v sub x? 2x. What is u sub y? 1. What is v sub y? Negative 1. All right, so you take this determinant. Well, 2x times negative 1, negative 2x. So then we subtract 1 times 2x. So we subtract 2x, giving us negative 4x. But now I say, remember, when we're taking Jacobian, we always really want the absolute value of everything because we're measuring dilation, which is some positive number. So our Jacobian is 4x. Now, what does that mean? Well, what this 4x tells us is that du dv is 4x dx dy. That's what the Jacobian is telling us. So the fact that we get 4x out is that 4x goes there. Now, why is that useful? Well, let's look at what we have. Here we have a 4x dy dx. So that says I can put those together, and those will become my du dv when I do my change of variables. Okay, so that 4x dy dx becomes du dv. All right? Okay, it's true. It's true. The same thing happens on this side. So now that we've done to Jacobian, let's talk about the function. Now, what part of the function do we need? The answer is we don't have to do the 4x anymore because the 4x is going to become part of our du dv. So the function that we have to focus on is the rest of it. So that part right there. So I have e to the power x squared minus y divided by 1 plus x squared plus y quantity squared. So what we look for is to say, okay, can I take my pieces u and v and use it to rewrite these expressions? So for example, e to the power x squared minus y, what can that become? It could become e to the v, because I see x squared minus y, that's v. How about 1 plus x squared plus y quantity squared? What can I do with that? That's 1 plus u squared, because u is x squared plus y. So I'm looking for those pieces, x squared plus y and x squared minus y, and I'm looking to use those to put them in. All right. Well, that's our function. That's our how we break things up. What's left? The bounds. Okay. So now comes the fun part. See, this is really two integrals. So let's do the first one. What do we know about x? 0 to 1. So let's say this is at 1. Where does y go from? Well, y goes from negative x squared, which looks like this. So here's y equals minus x squared, to where? Y equals x squared, which looks like that. Okay? So our first integral has that shape. So there's integral number 1. Integral number 2. Where do we go from? Well, 1 up to root 2 for x. Then we have, let's start with the bottom, x squared minus 2. Now, what does x squared minus 2 look like? It's a parabola shifted down. Let's figure out where we're at. When I plug in 1 into x squared minus 2, what's my y value? It would be at negative 1, right? Which means it's going to pass through that point. Okay, I'll put a little marker there. When I plug in root 2 into x squared minus 2, what's my y value? 0, which means it's going to pass through that point. Which means that it's a parabola that's coming up, it starts and stops. So there's that part of the parabola, okay? So that's the bottom bound. We go up to the top bound. So that is 2 minus x squared. So 2 minus x squared, it's a parabola that's been flipped over and shifted up. But to figure out where to draw it, put in the bounds. Where are we at when we plug 1 into 2 minus x squared?
1.
We're at 1, which means we're here. Where are we at when we plug in root 2 into 2 minus x squared? 0, which means that we're there. So it's this parabola that comes down and looks something like that. So that's our y equals 2 minus x squared. So our second integral is this shape. So there's our two integrals. Now the thing is, we don't have to translate as two separate integrals because we can say, look, it's really just one region. It's this one region which has these sort of 4 bounding curves. So we're not going to translate the two integrals individually. We're just going to say, what's the new region become? So let's talk about our bounding curves. We have 4 of them. So let's just work our way around. What are they? Well, they're y equals negative x squared, y equals x squared minus 2, y equals 2 minus x squared, and y equals x squared. Now, the way we're going to translate this into a region in the UV plane is we're going to write each one of these in terms of u and v. So we're looking for x squared plus y, and we're looking for x squared minus y. So what can we do? Well, y equals negative x squared, what can we do? We can add the x squared over, so this becomes x squared plus y equals 0. What does that tell us? U equals what? 0. Okay, how about this one? Y equals x squared minus 2. What does that do? Yeah, we can move the 2 and the y, have them swap places. X squared minus y equals positive 2. So what does that tell us? V equals 2. Okay, how about here? Y equals 2 minus x squared. Add the x squared. X squared plus y equals 2, which tells us u equals 2. Y equals x squared, what can we do? X squared minus y, subtract the y, equals 0, which tells us v equals 0. Now, the good news is, in the xy plane, it's these really curved things which are hard, but when we come down here into the UV plane, our curves are really nice. We have things like, for example, u equals 0. We have v equals 2. We have v equals 0. We have u equals 2. Which means that because of our substitution, our region translates into a square. So we're ready to put our pieces together. So integral, our function is e to the v over 1 plus u squared, and then we have du dv. Because remember, the 4x dy dx is going to become our du dv. Should we do du dv or dv du? Doesn't matter in this one because of our nice shape. What are the bounds? 0 to 2, 0 to 2. And this is one we can actually pull apart. 0 to 2, e to the v dv, 0 to 2, 1 over 1 plus u squared du. Integral of e to the v, e to the v, evaluate from 0 to 2. Integral of 1 over 1 plus u squared? Yeah, got to throw in there at some point. It's been a while. Good to see you again, arctangent. All right, plug it in. You get e to the 2 minus e to the 0, e squared minus 1. Then plug in arctangent of 2. That's arctangent of 2. And arctangent of 0 is 0. And there's the answer. And this would have been miserable to try to do the original problem, but we don't need to be miserable because we've got a better method. Now the same principles apply in 3 dimensions. So what do you have? You have a region, maybe in what we'll call UVW space, and then some sort of blob over an XYZ shape, and you want to go back and forth between the two. And so the only big difference here is the question is, what does your Jacobian become? And the answer is, well, what's happening is in 2 dimensions, we said, you have a parallelogram. And in 3 dimensions, what we have is that if we take a little tiny piece over here, so you have this little teeny tiny box, there's that little tiny box, then what it becomes like is it becomes like over here, approximately, not quite a box with necessarily perpendicular angles, but what we have is a box with parallel sides, parallelepipeds. And how do you find parallelepipeds? The answer is determinants. So the processes are just the same. Now the good news is we won't actually test you on that. Or maybe I shouldn't say the good news. The sad news is we won't test you on that. But now we can get an idea of what happens. So here we go. Suppose I want to find the Jacobian in rho phi theta, where x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z is rho cosine phi. Now if that looks familiar, it should. This is spherical coordinates. So what does the Jacobian say? Well, let's work this out. So we're going to take our various derivatives. So we're going to look at 3 by 3 determinant. We'll take derivative of x with respect to rho, x with respect to phi, x with respect to theta, and for all the other ones too, y with respect to rho, y with respect to phi, y with respect to theta, z with respect to rho, z with respect to phi, and z with respect to theta. So we start populating this. It's going to be 3 by 3. So I'm going to take derivative with respect to rho. Well, we'll get sine phi cosine theta. X with respect to phi, that'll be rho cosine phi cosine theta. X with respect to theta minus rho sine phi sine theta. Okay, that's our first column. Y with respect to rho, sine phi sine theta. Y with respect to phi, rho cosine phi sine theta. And y with respect to theta, rho sine phi cosine theta. Now that's our second column. Our last column, there's a lot. Okay, cosine phi, that's the derivative with respect to rho. Then minus rho sine phi, that's the derivative with respect to phi, and 0, no theta. Now, if we take this determinant, well, let's do it. So, remember, we just go down. Sine phi cosine theta, rho cosine phi sine theta, 0. Woohoo! 0. Good. Okay. Sine phi sine theta minus rho sine phi, then minus rho sine phi sine theta. What does that turn out to be? Well, if we look, there's a minus rho, that makes it a rho squared. There's 2 sine thetas, so, and there are 1, 2, 3 sine phi. So, all right, this is sine cubed phi sine squared theta. So that's 1, 2, 3. Next, cosine phi, rho cosine phi cosine theta, rho sine phi cosine theta. So we have two rows, so that's rho squared. For phi, we have sine phi and cosine squared phi. So sine phi cosine squared phi, and we have cosine squared theta. All right, next up, so that's the 1, 2, 3. So those are our down. Let's go up. So we're going to subtract when we multiply these two terms together. But because of that minus, it's going to actually be another plus. Now what do we get? There's going to be two rows, so a rho squared. We're going to get two cosine phis and a single sine phi. So I'm going to put this here as we get rho squared. We get sine phi cosine squared phi. And then we have two sine thetas, so that makes it sine squared theta. Then the next term, multiply this, this, that, those three terms. Well, we're going to subtract. Because of the minus, becomes a plus. Still we have two rows, rho squared. Then we have sine phi, sine phi, sine phi. So that's a sine phi cubed. And then we have cosine theta, cosine theta. So that's cosine squared theta. Okay, so that's what we end up with. Now, if we survived, of course we survived. No problems, no problems. What do we have? Well, notice everything has a rho squared. Everything has a sine phi. Rho squared sine phi. Sounds a little familiar. What's left? Well, from the first term, we have a sine squared phi, sine squared theta. Then from the next term, we have, well, let's not go in order. Let's do this one. Now let's jump ahead to that one, the last one. That's a sine squared phi, cosine squared theta. Now we'll jump back to here. We have a cosine squared phi, cosine squared theta. And finally, from here, we have a, well, not quite enough space, but cosine squared phi, sine squared theta. Now, if you look at the first two terms here, you say, oh, you can pull out a sine squared phi. Then you get sine squared theta plus cosine squared theta. But this is 1. So that says the first two terms are sine squared phi. From the next two terms, you can say, oh, here you can pull out a cosine squared phi. And you're left with cosine squared theta plus sine squared theta. But that's 1. So this becomes cosine squared phi. But sine squared plus cosine squared for phi is 1. Which means what's left is rho squared sine of phi. And therefore, what do we conclude? Well, we conclude that dx, dy, dz is our Jacobian term, which we can say is rho sine of phi, d rho, d phi, d theta. So that justifies what we did last time. So now we know where that rho sine of phi comes from. It comes from our Jacobian. Good. So, good news. If you ever forget rho squared sine phi, easy solution. Just take this determinant and boom, it pops out. Well, probably it's better. Don't forget rho squared sine phi. Yes, I prefer that solution. That sounds like a good option. All right, let's do a little bit more practice. Because the more we practice, the better we get. So let's evaluate the following integral. And it's 1 to 2, 0 to 2 minus y, 2y cosine of x plus y cubed minus 3 times x plus y dx dy by setting u equal x plus y and v equal y squared. Well, the good news is it's not so hard to find the substitution. There it is. They told it to us. Aha! So that saves us a little bit of work. Next up, let's take our Jacobian. So we get ux, uy, vx, vy. Take our 2 by 2. All right, u sub x is 1. u sub y is 1. V sub x is 0. V sub y is 2y. It's telling us that our Jacobian is 2y. Now, what does that tell us? Well, it says that if you take 2y times dx dy, that's the same as du dv. All right, so that's our conclusion. Now, how do we use that? Well, notice what do we have? We have a 2y dx dy. So these parts here are going to become our du dv, or possibly our dv du. It just depends. We'll figure that out as we get closer and look at our region. Now, let's look at our function. So the function says, let's look at the part that we don't need to use our substitution for. So we're looking at this part right here. We say, okay, so we need to look at this function. Cosine of x plus y cubed minus 3 times x plus y. And what we're looking for is how can we rewrite this expression using u and v and not x and y. Well, there's a big hint. This is in terms of x plus y, and that's what u is. So this becomes cosine of u cubed minus 3 times u. And there you go. All right. So we've now done our Jacobian, and we've done our function. The last thing to do is to do our bounds. So let's think about our bounds. So currently, we have that y goes between 1 and 2, and then we have that x goes from 0 up to 2 minus y. So we say, all right, let's see what this becomes. So our picture here, well, here's 1 and 2, and x equals 0 is this part, and 2 minus y, well, let's see, what is that? That tells us it's a line. Now, x equals 2 minus y, if you're not sure how to draw that, you could actually swap. It's the same as y equals 2 minus x. So you're coming down, because you have an intercept at 2, slope of negative 1. And we go to there. So this is y equals 2 minus x. And the last part is y equals 1. So there's our region. It's a triangle. So we say, all right, good. Life is good. Life is good. We've got our shape. Now, we're not done yet. What do we need to do? We need to translate our bounding curves. So we're going to take each one of our bounding curves and rewrite it. So this curve, y equals 2 minus x, that's the same as saying x plus y equals 2. And that one's pretty straightforward. X plus y equals 2 tells us that u better equal 2. Y equals 1, well, that's not so bad. We look in here, we say if y equals 1, then that tells us that v equals 1. 2 for 2, straightforward. Now, what about x equals 0? Now here, it's not so clear. But let's take a second and say, well, what is true if x equals 0? So if x equals 0, what you get is that the first equation says u equals y, and the second equation says that v equals y squared. But wait a second. If v equals y squared and u equals y, I can put those two together and get to the conclusion that v is equal to u squared. So those are our bounding curves. U equals 2, v equals 1, v equals u squared. Now, what does that look like? Well, so let's come here. We have our u, v plane. And let's see, we have v equals u squared. So that would be our parabola. We have v equals 1, which, okay, here's v equals 1. And then we have u equals 2. Now, what is u equal 2? Well, u equals 2 is, curiously enough, way over here. All right, well, that's kind of curious. Okay, well, it is what it is, right? So u equals 2. And, all right. So, what's our region? Well, it's this one, right here. It's another triangle. Of course it should be a triangle of some sort. Now it's not a triangle, though in this case, triangle, this is all flat. Here, this part is curved. All right, but that's all right. No problems, no problems. So we have v equals 1, all right, underneath here, u equals 2, and we have v equals u squared. So now we're ready to do the integral, because it doesn't just say rewrite it, it says evaluate it. Okay, integral. So the 2y dx dy becomes our du dv. Then our function becomes cosine of u cubed minus 3u. Now we have to choose, is it du dv or dv du? And look at this, it's like, it's not going to be du dv. No, we refuse. We're not going to integrate. Why? Well, because you can't integrate that with respect to u. But you can with respect to v. So dv du. All right, no problem. Where does u go from? Well, we start at 1 and we go to 2. 1 to 2. Where does v go from? Well, if we have a value for u, what happens is we start at this curve, v equals 1, and we go to v equals u squared. So it's from 1 to u squared. Okay. So we integrate 1 to 2, then we get cosine u cubed minus 3u times v, evaluated from v equals 1 to v equals u squared. So that's the integral from 1 to 2 of cosine u cubed minus 3u times, well, plug in u squared minus 1. Now we say, that's not so bad. It's kind of interesting. U cubed minus 3u, and there's a u squared minus 1. We might be thinking of some sort of a substitution. So let's think about that. Let's suppose we were trying a substitution. Now we already have a u, so we're going to go up to the next one. We'll call it double u, because it's a double substitution, right? So double u cubed minus 3u. dw is 3u squared minus 3 du. And if we divide everything by a third, we could say that 1/3 dw is u squared minus 1 du. So that's perfect, just what we need. So what we get is we have the 1/3 coming out. So this becomes 1/3 integral of cosine w dw. Now the last thing to do is, what are the bounds? So you plug in. If you plug in 1, you're going to get 1 minus 3. So that's negative 2. And if you plug in 2, what do you get? Well, you're going to get 8 minus 6, which is positive 2. Now, cosine is an even function, which tells us that we can just double the integral from 0 to 2. So integral 0 to 2, cosine of w dw. So we're almost there. Integral of cosine is positive sine. So 2/3 sine of w, that's a w, from 0 to 2. If you plug in sine of 0, you get 0. So our final answer is 2/3 times sine of 2. And that's our answer. There you go. Okay, so not so bad. So substitution helped us out yet again. Who would have thought? Well, probably everybody who's doing the problem, because if it didn't help us, we wouldn't have done it. Well, let's try one more. So let R be the region with the absolute value of x plus the absolute value of y less than or equal to 1/2 pi. Find the integral over this region of cosine x cosine y dA. And it says, oh, there's a hint. Now, don't know why we need the hint, but okay. That's all right. We'll get back to that in a second. Now, what's our region look like? Now, this is kind of a different way to write it. absolute value of x plus absolute value of y less than or equal to 1/2 pi. And what it is, it's a diamond shape. So one of the things you might learn about, there's different ways to measure distance. This is what's sometimes in math parlance it's called the one norm, where the distance is just the size of your values. So you want the size of x plus the size of y to be at most 1/2 pi. So for instance, there's an intercept here at pi halves, because there x equals 0, y equals pi halves. And similarly down here at pi halves, negative pi halves, and at negative pi halves. And what happens is, depending upon which quadrant you're in, you change your sign. So for example, if I'm in the first quadrant, it's x plus y equals pi halves. Say I'm down here, well, that would be, I want positive x minus y, because y is negative in that quadrant, equals pi halves. Over here, well, now it would be negative x plus y should be pi halves. Downstairs, well, they're both negative. Minus x minus y equals pi halves. And there we go. That's our region. So this is our original region. Now if you look at this, what you have is you have a square that's been turned on its side. So it's a diamond shape. Okay, so that's not so bad. Now the thing that hasn't been done here is they haven't told us what the substitution is to make. But we can see that our region is very suggestive. And so in this case, because our region has these nice lines that run at 45 degrees to various normally, what we'll say is, okay, let's do the substitution. U equals x plus y, and then we'll have the other substitution be x minus y. All right, now again, normally we'll give you the substitutions, but this is sort of the logic about how would you go about looking for something. So let's do our Jacobian. So we're going to look at u sub x and u sub y and v sub x and v sub y. And if we do this, what do we get? Well, we get u sub x is 1, u sub y negative 1. Let's see, is this right? Yeah, that's fine. V sub x is 1, and then what do we have here? Wait, I did this wrong. That should be u sub y. That's plus 1. I looked in the wrong place. U sub y. V sub y is minus 1, which is minus 1 minus 1. But of course, when you take Jacobian, you're looking at how much is dilation and contraction, so you end up with 2. Now, what does this 2 tell us? Well, what this tells us is this is really saying that du dv is equal to 2 dx dy. Because this should really be thought of as a function involving x and y. Because these are really coming from derivatives of functions of x and y. So this 2 goes with the dx dy. Now there is no dx dy here. So this dx dy, that's our dA originally. So when I do my setup in my new region, I'm going to say, okay, my dA is going to be 1/2 du dv. Okay, so converting, that's what we're going to have. So essentially, we're going to have a contraction going on. All right, now what happens? Well, we need to figure out a couple of things. What's our function going to be? Well, we got to figure this out. Now, cosine x, cosine y. I want to write in terms of x plus y and x minus y. Now, it's not so obvious what to do unless we say, there was this hint here, which says cosine x, cosine y, that's 1/2 cosine of x plus y plus 1/2 cosine of x minus y. Oh, that's very convenient. Because this becomes 1/2 cosine of u plus 1/2 cosine of v. So that's our function. Woohoo! Nice. Progress. So we're making great progress. We've written our function in terms of u and v. We've gone, how do we change our area? Life is good. What's the other thing we need to figure out? Well, the other thing is our bounds. And so we've drawn our region here. So we just need to go through and figure out what are our new updated bounds going to be. So we go through and rewrite things. So our current bounds, our bounding curves, x plus y equals pi halves. We also have the one right across from it would be, if we multiply both sides by negative, x plus y equals negative pi halves. Here we get x minus y equals pi halves. And the one straight across from it, if you multiply by negative, x minus y equals minus pi halves. And these become nice to translate. U equals pi halves, u equals negative pi halves, v equals pi halves, v equals negative pi halves. Which tells us that in terms of our uv plane, remember this over here is our xy plane, but in terms of our uv plane, we're now a rectangle. And we're going from pi halves to negative pi halves in both directions. And there we go. Okay, so that's good. And the nice thing is, because it's a rectangle, our bounds are really going to be very pretty. They're going to be nice and simple. Unlike the bounds here, where we'd have to do a couple things. In fact, we really couldn't do this as one integral, because we have this changing behavior whenever we cross through either the y-axis or the x-axis. Now we can definitely do one integral. Indeed, there's no surprises left. So let's see what we get. We get the following. Well, we're going to have that our integral over our region of our function cosine x cosine y dA is going to be equal to, so we have integral. We'll do our bounds in a second. Our function is 1/2 cosine of u plus 1/2 cosine of v. So there's our function. Our dA is 1/2. And now we have to say du dv. In this case, it doesn't really matter. It's just a rectangle. There's no clear preference. Negative pi halves to positive pi halves, negative pi halves to positive pi halves. All right, a half can be pulled out of both these terms, and there's another half, so I can write this as a 1/4, and now we integrate the first layer. Well, when you integrate the first layer, that's integrating with respect to u. Integral of cosine becomes sine, and then plus cosine of v times u. And that's evaluated from u equals negative pi halves to u equals positive pi halves dv. Now I could have probably saved myself some work by saying, oh, wait a second, I actually have a lot of symmetry here. But, oh well, live and learn, as they say. Okay, so what does this turn out to be? So 1/4 negative pi halves to positive pi halves. Now when we plug in sine of pi halves, you're going to get 1. But then you're going to subtract in sine of negative pi halves, which is negative 1. So 1 subtract negative 1 makes this 2. Then you're going to have cosine of v, which is going to stay as cosine of v, times pi halves. Then you're going to take cosine of v, subtract negative pi halves. So what you end up with is pi halves times pi halves subtract negative pi halves, which is pi. So pi cosine of v. All right, we're integrating that with respect to v. So what do we get? Well, this is 1/4. And now the integral becomes 2 times v plus pi sine of v, because that's the antiderivative of cosine. And we're going from negative pi halves to positive pi halves. Well, 1/4, when we plug in pi halves, we'll get pi. And then when we plug in negative pi halves, we'll get negative pi. So when we put those two together, pi subtract negative pi will give us 2 pi. Now here, when we plug in pi halves, we'll get sine of pi halves, which is 1, times pi, so we get a pi. When we plug in negative pi halves, we'll get negative 1 times pi, which is negative pi. So it's again pi subtract negative pi, which is another 2 pi. 2 pi plus 2 pi makes 4 pi times a fourth, leaving us with the final answer of pi. And that's it. We're done. It works. Okay, cool. Now, a couple of comments. This is one you probably could have done without substitution. Oftentimes you can do these problems other ways, but we want you to get the practice of doing this because there will come times when you aren't going to be able to make progress. The 1/2, by the way, you can kind of see from the picture what's happening. If you were to take this shape, you could actually squeeze it into here, and if you look at it, it would fit right here. And it turns out that if you stare at this for not very long, you say, oh, wait a second. The original shape is half of the size that the new shape is. So that there's this dilation going on, and so that you're really scaling your areas by 2 when you do this sort of rotate by 45 and expand. So that's where that half is coming from. You can see it takes half the area that the new shape does. So that little piece in the original shape is half as big as what it would be in the new shape. All right. Well, don't worry. You'll get more practice on this. So keep practicing and you'll get better. All right, that's it for today. See you next time. Bye.